Hi everyone and welcome to episode 9, I believe this is, of eCHO, the eBPF and Cilium office hours. I can see Michael was the first into YouTube chat already, great to see you. And we also have Christopher and Quentin who've joined us as moderators. If you are joining us live, do say hello in the YouTube chat. We love to hear from you, and that's also the way we'd love to get your questions. So today is going to be a very exciting episode. We're going to be talking about XDP with Daniel Borkman, who is a kernel maintainer and a specialist in eBPF and XDP. But before we get into that, let's have a little look at the headlines for this week. And there is really big news this week. We have announced the dates of the eBPF Summit, which is going to be happening on August the 18th and 19th. So there is a form that you can fill in to pre-register. It's there at ebpf.io/summit-2021. That's going to be the landing page with all the information about the summit. But if you pre-register, we will keep you in the loop with emails. So we're hoping to see everyone who joins us on eCHO do come and join us at the summit as well. And the CFP will be opening very soon. All right, so hi to Alberto Jimenez. Thank you for joining us. Also, it'd be really good to hear, where you're all viewing us from. That's always really interesting to hear where you all are. All right, the next headline that we have is actually a post on LWN that Quentin, who is with us today, has written to describe what's happening in the implementation of eBPF for Windows. Okay, viewers from Barcelona in Spain, that's great. I feel like we should say hola. Oh, and Paris, bonjour, excellent. And Ottawa. I'm not sure if Ottawa is French speaking or English speaking, so yeah. Hi Noel, hi John, thank you for joining us. So yeah, let me just give a little bit more of a shout out to this really great article that Quentin's written about the eBPF for Windows implementation. Next week, it's going to be in the later slot, like 5 hours later than this one, but we will have a special episode about eBPF on Windows with Dave Thaler. So if you're interested in Windows, do come and join us for that. I think that's going to be fascinating. And the background that Quentin's written here is going to be really useful for me to understand what's going on in that project. There's another great post here as well about Netflix using eBPF at scale. I think we all know that Netflix is probably one of the heaviest traffic sites and one of the early users of eBPF, particularly through Brendan Gregg. So that is a really good article to read about how they've been using eBPF flow logs. And another headline or project that we wanted to share was this HBPF, so eBPF running on FPGAs. So that's a pretty interesting development. Now, it actually turns out, I didn't know this, but there is another hardware project for eBPF. And if we have time, we will mention that later. There's a project called XDP, which I think has been around for a while. So yeah, eBPF implemented in hardware. It's pretty exciting, I think. All right, hello. We have lots more people who've said hi. So hi to Marius from Germany, Bom dia from Gustavo from Brazil, Raul from India. Okay, Ottawa is bilingual. That's. I need to know that. I should know that. Khalid, hey, Russell, hello, and Yarin joining us from Israel. Great to have you all with us today. So, without further ado, I think we should move on to the main topic for today and introduce our guest. So, please put a big sort of virtual round of applause together for Daniel Borkman from Isovalent, who is kernel maintainer, officially a co-creator of eBPF and a specialist in eBPF on the data path and XDP. So welcome to eCHO, Daniel, and thanks for joining us today.
Hello, thanks for having me on the show.
And now I'm going to just tell the audience we've been collaborating on some notes for like what we can talk about today, and there is so much here. There is so much material we can talk about. So if we don't get through everything today, we may have to invite Daniel back in the future, but I think there is a lot of really interesting content here to talk about. Please do ask your questions as we go along. Also, let us know if there's anything weird about the audio mix or anything like that, and we'll try and get that fixed. So, Daniel, our topic for today is XDP and load balancing. So I think we should start by tell us what XDP is.
Yeah. So, and by the way, feel free to interrupt me at any time if you have questions or so, or if I should go into some details. So XDP, Express Data Path, that's basically a layer in the kernel, in the Linux kernel, in the networking data path. And it's basically a layer where you can mangle network packets, where you can redirect them, drop them, and that's at the earliest possible point in the software stack. So basically, a network packet arrives in the hardware, and then the driver processes that network packet. And even inside the driver, there's a BPF program that can be attached to the XDP layer. And it can then change the packet and drop it, as I mentioned. And from then, after that, it could decide to, for example, push it further up the stack or, do other things with it. So that's like really the earliest possible point.
So does that mean it needs support from the network card to work?
Exactly. Yeah. So you need to have, we call this native XDP, where basically a driver has support built in, because the way the driver has to operate in the XDP layer is slightly different compared to the regular networking stack. Because here, when a BPF program is operating on the network packet data, it is able to read and write into this data, and that is normally working differently for the rest of the stack.
And it probably just sort of worth mentioning, but every time we copy data, maybe copying it out of the network card and into kernel memory, or maybe if we were copying it again from kernel into user space, every memory copy is like a pretty costly operation. So by avoiding copying memory and deciding what to do with these network packets, that's gaining us performance, right?
Yeah, I mean, usually for in the non-XDP case where the drivers operate, they have like this network data is read-only in a page, and then pull this into its so-called working area or linear buffer, and then you can access and change it. And so yeah, I mean, you don't have to copy everything in at once, but it's like just bit by bit. But in the XDP case, you don't need it.
Right. So one thing that I think is interesting when we think about XDP, taking the packet as close as it can to the physical network interface, is it just faking it if we have a virtual network interface?
It depends. I mean, there's, for example, support in the kernel where you can redirect a network packet that arrives from the physical NIC where you have native XDP, and then you can redirect it into a container weave device. That is possible, and that container weave device also operates in the XDP mode. And from there, it would have to create like a regular socket buffer for the kernel networking stack and then push it up the stack. There's also support for VMs if they don't have something that is called SRIOV, which is like where you can split let's say a physical device into, or like you can slice it into several virtual ones as well, and then move those into the containers to operate at native speed. If you don't have such a support, there's also word.io.net in the kernel that supports the native XDP case. It's still fast, but not as fast as if it's like a native driver.
Right. All right. So tell us a bit about the history of like how XDP was thought up.
Yeah. So for the history, we have to go a little bit back a few years, like into 2013, let's say. So back then, what you can see as the SDN landscape in the Linux kernel networking stack, I would count like the Open vSwitch, TC, and NetFilter as like the tools where you can change packet data and like do interesting stuff with it. Back then, like all of those three subsystems, I mean, they still exist today, of course, and they're still to some degree extended today. But they were sort of competing with each other, but you don't have like a full programmability. So you basically the data path kind of needs to know what you're going to do with it. So you have like built-in functions that do certain things, and in contrast to eBPF, for example, where eBPF, with that, you can create the data path itself. It was not there back then, right? And back at the time, I mean, there's always discussion and arguments about feature creep. Whenever someone adds something interesting that is maybe only interesting to them or to a few people, but still it affects everyone else because it's in the fast path of the kernel. You try to, I mean, there are like tough arguments sometimes on the kernel list because you don't want to slow everyone else down. And at the same time, back then in 2013, actually, there was also DPDK, which was there, like it was like 1 year old at that time. And it was making some headlines, you know, like with DPDK, you can process millions of packets per second in user space, and kernel is too slow, and so on and so forth. So back then I was at Red Hat and after that Cisco, and there we had like a working group where we tried to improve the core kernel networking data path, make it faster, come up with ideas to optimize it. That's all nice and good, but like it's not like it didn't reach or like the DPDK speed that is like desired. And yeah, like in 2014, actually, we merged eBPF, like the very initial bits of eBPF into the kernel. Alexia was back then, Alexia Starovaitov, more focused on the eBPF tracing bit and myself on the networking side. And that basically already was like a big leap forward because you can fully like program the data path. Of course, like back then it was more, it was not as flexible and usable as it is maybe today. But like still, it was like a starting point and it was like fundamentally different than the rest because you had much more flexibility. 2014 actually was also where there was the initial commit from Kubernetes.
Oh, yeah.
for those who don't know. So that's an interesting data point where things started. And in 2015, I actually added an extension where you could run eBPF programs inside the TC data path. And I will probably it makes sense if I shortly share my screen because here that's like a paper on XDP that we did with some colleagues in 2018. And in here, there's an interesting overview graphic. So what you can see here, there's the networking hardware down here. Then we have the Linux kernel part. And up here, the user space with applications or containers, VMs, and so on. And the TC bit is what you can see here, like in this blue box, TC BPF. So basically, we extended TC to run eBPF programs. And also we added like, there was already an existing ingress hooks, which would see all the network traffic coming in. And we also extended it to have an egress hook where it would see all the network traffic that is going out of the node. And yeah, with that, actually that is still like some of the core base that Cilium is using nowadays. It's flexible because it operates on socket buffers in the kernel. You can read all the metadata from it and so on. But still, like, it's still not as much, for example, speed as DPDK. And yeah, so back in 2016, actually, there was a conference, NetDevConf 1.1 in Seville. And back then we did see, of course, like the potential of TC, BPF, and trying to make it more popular, giving talks and like, you know, but I think Thomas, Alexei, and myself, we were like still like in one of the breaks in there, and we were brainstorming. So like, is there anything we can do like fundamentally to, change it? And I think we were just like joking about, yeah, I mean, so why don't we just put BPF inside the driver, like really the lowest possible point. And actually after the conference, Alexei and also Tom Herbert, they took this away and like they formalized the idea further. And with the help of some other folks, they started an implementation of what is nowadays like the express data path. And starting with I think it was a Mellanox driver back then, which was 10 gigabit, I think. And yeah, and then in 2016, this was basically merged, like I think in autumn it was. And that really shifted, I think, also the perception of people that maybe the kernel is too slow for some of the use cases. Basically, the concern was back then from networking maintainer, also from David Miller, that, for example, DPDK is like potential. It has potential that it would drive away the innovations maybe from the core kernel networking. It would also like fragment the networking landscape. And it would be good to have a solution that is also like inside the kernel. And actually, many years later, I also talked to the DPDK maintainer, which is Thomas Manjalon. Sorry if I pronounced the name completely wrong, but and he actually gave me also his perspective. And his concern was basically that that DPDK has so many user space drivers and there's so huge code constructs that there's like a bloat in terms of the drivers. And also like the DPDK tooling is starting like to copy or like some of the concepts from the kernel tooling. And he's like concerned with duplication. And he was not necessarily like against the, I don't know, like kernel networking, but just like it didn't offer like a fast enough networking solution. And for many years, like the Linux kernel only had AF packet, which is used by TCP-dump, for example. There were attempts to upstream different solutions, for example, NetMap, that is part of also a FreeBSD, but they all got rejected. And later, actually, it was in 2018, Intel developers, they developed AF-XDP, which is basically an XDP extension. You can see it here, where you still have the BPF program running inside the driver, and then it can redirect the packet into a network socket. And then user space has like the zero copy ability and similar to DPDK, just that you have those drivers inside the kernel, and the goal is basically to have like 90% DPDK speed.
We got a couple of questions came in, and sorry, let me interrupt you quickly. So one actually really kind of fundamental question is, what exactly is the data path? Does it mean data flowing from physical interface to an application?
Yeah, exactly. Yeah. I mean, data flowing from a physical interface maybe to another physical interface when you do forwarding, or into an application, which in that case means like a local socket that an application has for connecting to the outside world. So it's like either like traffic going into the node, into an application, or coming from an application and leaving the node, or like forwarding, for example.
Right. Yeah. So we should think about data flowing into or out of an application, and we want to try and shift that as quickly as possible, or possibly, we don't even have anything to do with it on this machine. We just want to get it in and out of the machine as quickly as possible.
Exactly.
So another question/comment from Yarin. DPDK and Cisco Trex traffic generator. Flame emoji. I wonder if XDP and eBPF will have such an implementation for traffic generated by or simulated. So yeah.
That's a great question. Short answer is, or like, maybe not so short, but like in the Linux kernel, there's no transmission path that is like native XDP for applications that are sending things out of the local node. The reason is because the kernel by default like handles socket buffers, or like works on socket buffers. So like converting from a socket buffer, for example, to an XDP representation of the packet would be too costly. So that doesn't make sense. There are packet generators inside the kernel, for example, packetgen, which also operate on SKBs, but they are not as fast as like the packet generator from DPDK. But there is something that is called, as I mentioned, AF-XDP, and that also has like a transmission path. And in fact, AF-XDP is one of the drivers for DPDK. So you can basically use that as a backend so that you can reuse all the in-kernel network drivers as well. And with that, you can also use your DPDK-based packaging.
So question from Marius, as XDP is in the driver, are there still hardware interrupts to be handled? Is polling on a dedicated core a driver setting?
I actually wanted to go into that a little bit later, like how is it different from DPDK, but the short answer is, I mean, it is running inside the driver. So basically that's like, so the packet is basically pushed into one of the receive queues of the network card. And then later on that packet data is picked up through the NAPI mechanism, which is like a polling mechanism where the software interrupt calls into the driver, and then it tries to process as many packets as possible. And from there, we do call into the XDP program and how you want to orchestrate that, for example, whether you want to do busy polling or whether you just want to rely on the standard NAPI scheduling that the kernel has, that's completely up to you. And in many cases, it's actually sufficient to just rely on the standard NAPI mechanism to pick things up, unless you really want to burn every possible CPU cycle and pick it up as fast as possible with the lowest latency as possible. And how you basically partition how that traffic is processed on which CPU, etc. So that is also like up to you, and you can configure this through the scheduler.
So what's the kind of landscape today in terms of XDP, DPDK? Do both those kind of continue to exist? Yeah. And clearly XDP is still undergoing lots of innovation. What's the situation with DPDK?
Sure. I can go a little bit into the use cases because I don't think there's only focus on DPDK. Like XDP has many other things to offer. For example, we see many layer 4 load balancers. Like I will go into that a little bit later. There's Catran from Facebook, there's Unimog, Cloudflare, and in the latest Cilium release, we also added a layer 4 load balancer on the XDP layer. That's one thing, because like XDP really shines when you get the packet, you process it at the XDP layer, and then push it out as fast as possible in the driver layer itself. So typically, you can have like a hairpinning load balancer, like just being pushed out from the same NIC or a different one. That's one thing. And also what often goes along with that is like the DDoS protection. Because you're at the XDP layer, you can drop packets as fast as possible. We recently did a test, actually, me and my colleague, on the 100 gigabit NIC, where actually DPDK packet chain was pushing as many packets as possible from one node to another. And like, I think it was generating around 117 million packets per second or so. And like XDP was dropping that many as well, if you, yeah. So right. Like you can, it's really suitable for, like policies and wasting as little CPU cycles as possible, compared to when you do this at the later parts of the network stack, for example, like NetFilter or others. The other thing where this also shines, and I think maybe this is not too often talked about, is hardening, like kernel hardening, for example. For example, like the layer that comes right after XDP, when you build the network packet, like the regular SKB, push it further up the stack, that's the GRO layer. It's called generic receive offload. And that is basically parsing the network packet and trying to aggregate many small packets into a super packet. For example, think of TCP. You have usually like a train of packets of data packets coming in, and they're maybe like 1,500 bytes, like typically MTU sized, and you can aggregate those up to 64K, up to a super packet of that size, and then you only need to push that super packet up to the stack into the socket. So that's like a performance optimization. And there are also support for various other protocols, but basically this layer already is fairly complex, GRO layer, and it needs to parse packets. And yeah, what happens if you have like a bug in there, right? And so kernel hardening here in that sense that with XDP you can instead of having to, you know, like when that really, I mean, luckily those bugs are really rare. But when that happens, then everything is on fire, of course. And because like a remote attacker could kill your entire node with a bad packet. And with XDP layer, you don't need to like upgrade the kernel, reboot, and, you know, like as fast as possible and re-roll everything out to have that security bug fixed. But with XDP, you can simply just like have a policy and you just drop those packets. If you would do that with, for example, net filter, which is at the later layer, for example, here, like the IP layer, or like shortly before the IP layer, you already have to go through your GRO stack, and you already have to go through various packet parsing functionality, right? And the same is so like it's not only GRO, but the same is like in all the different complex layers of the kernel networking stack. It can be like when the kernel is trying to calculate the packet hash, for example, it also goes and parses. And actually, we did have a bug in that area where there was like a possibility of a packet of death type scenario, but this was like long ago. I think it was like 2000, maybe 13 or so. I don't know. Like I would have to look it up, but it's not like it's impossible. And even like in the net filter case or like upper protocols, these things can happen, right? And there you have like an ability to immediately react and change things on the fly without having to reboot, without having to even interrupt traffic that is like going into containers or pods. You can just do this atomically.
Yeah, like never mind having to load a new kernel module or upgrade the whole machine. You can just dynamically load the patch on the fly. It's amazing. In fact, Yaron just said security virtual patching. Wow, that's awesome.
Yeah. And yeah, so you have basically the hardening, the DDoS mitigation use cases, load balancing. You can also do like stack pre-processing, because like at the XDP layer, there are no assumptions that you have to make when, for example, you have like a regular socket buffer. Those things are more tied into protocols. It's like a little bit more difficult to change things on the flight, like to mangle packets, to decapsulate and so on, or like to add encapsulation headers. For example, you could have like your, I don't know, custom encapsulation. You would decapsulate at the XDP layer, and the stack could still aggregate this in the GRO layer when you strip the data off from XDP side, right? And you can then propagate information with BPF to upper layers in the stack. That's possible as well. That's maybe more like a niche use case, but yeah. And then you have the AF-XDP with the DPDK that I mentioned, and but of course also monitoring or IDS, right? It's not like, for example, there's Suricata IDS that was for many years using AF packet, and they switched to XDP, and yeah, it's like significantly faster to do it there. So yeah, there are various use cases.
And in fact, since we just mentioned being significantly faster, I think you had some illustrations of performance that you wanted to show, some performance graphs.
So I think it was 2018 or so. 17, sorry. Basically, Facebook decided to migrate from their existing IPv6-based, so net filter-based layer 4 load balancers. They basically had back then dedicated boxes to do all the load balancing for traffic that is going to facebook.com. And back then they decided to migrate that to XDP and BPF. and to, like throw everything away and like try that and see how fast it goes. And what you can see here, like they didn't publish explicit numbers in terms of packet per second, but they showed like actual production traffic. And what you can see here in terms of packet per second on the lower graph, that's like the IPVS based load balancing that what they were processing. And this up here, like the upper graph here, is what they saw with XDP. And they said that it was like an improvement in some cases of up to 10x that they noticed. And at the same time, their CPU overhead reduced significantly as well. So again, like the lower graph here was like I think that might have been here XDP and or like the CPU idle, sorry, yeah, the CPU idle. So yeah, that really improved quite significantly. And that was 2017. I mean, since then, many others also adopted and migrated away from, for example, IPVS and are using XDP, especially given there are open source solutions for layer 4 load balancing available, like Catran, or recently also like the Cilium layer 4 load balancer, and that facilitates things significantly. And that's a big leap forward in terms of load balancing.
Maybe that's a good lead into talking a little bit about Cilium's use of XDP in particular. Well, we can talk about it a little bit in general, and then we'll talk about the load balancer side of things.
So, sure. In case of Cilium, we basically initially we originally replaced the kube-proxy layer, which is handling all the Kubernetes service traffic, and we changed this and ripped out like the net filter functionality and do everything in eBPF. And originally it was like designed for the TC layer, like the TC BPF for the north-south load balancing handling. And in the Cilium 1.8 release, which was like mid last year, we also extended this to XDP. And the interesting bit here is what you can see here, like that with that we can operate, like as close as possible for the north-south case to the driver, and that gives like all the performance benefits. In case of kube-proxy, how does that look? Basically, there are different services like Nodeport or the load balancer service and various others. And whenever like a packet arrives on the node and that node realizes that the backend is on a remote node, it needs to push the packet back out from the network card, right? And you can do that.
The backend being one of the pods that services that service, or that provides that service.
That is residing elsewhere, yeah. Exactly. And then it can push it back out right at the XDP layer as fast as possible. So in that case, it's basically, like looking up the service VIP, it's figuring out which backend to use. There's like a connection tracking table in eBPF and also network address translation that we do. And for example, it could pick a backend, maybe randomly store it in the connection tracking table, then do the DNAT translation, so where you basically translate from the service VIP to the backend IP import, push it to the backend, and then the reply comes back into to that specific node. It does all the things in reverse and push it back to the client. Later on, we also extended this to DSR, which is called direct server return, where you don't have this extra reverse hop through that original node. So the backend can push the traffic directly to the client, which improves the latency. And yeah, so
the request comes in, goes through the load balancer to a backend, and then the backend can reply directly to the client, sort of skipping the load balancer on the return path.
Exactly, yeah. And basically, like the way we did that is because we had everything initially implemented for TC, where it has like slightly different helper functionality and it's slightly different to program, but we basically have we abstracted that layer so that the same load balancing code mechanism can be compiled to either eBPF layer or XDP layer, which gives quite some flexibility. And if you improve one thing, the other one benefits automatically as well in Cilium.
Maybe you could just talk a little bit about TC. So TC is presumably inside the kernel rather than kind of in the...
Exactly.
Yeah.
Yeah, so that's like, once the, like, it's definitely higher than the XDP layer. So basically the kernel first has to allocate a socket buffer meta structure. It then has to populate it with the information from the driver, and then it pushes the packet through the GRO engine for the aggregation, what I mentioned earlier. And right after that, you still have TCP dump in case there's like some TCP dump session active where you want to record traffic. But after that, there comes the TC ingress hook in the kernel. And from there, it basically operates in socket buffers. It can forward this to Weave devices or like other devices in general in the kernel and push it into the pods or containers. And basically that TC layer, it can also move the traffic back out. But it's definitely more overhead needed, more cycles needed to prepare everything and to get into that layer compared to XDP.
Right, yeah. I'm just going to briefly say I missed them coming in earlier, but hi to our regular viewers, Alex and Magno, who've joined us. So good to see you again. Right, so where were we? We talked a little bit. Is there anything else we should say about kube-proxy, or should we move on to north-south load balancing?
I think I still wanted maybe to clarify some facts on, like in terms of XDP versus DPDK. I think that might be interesting.
Sure.
So people think like XDP may be a kernel bypass or so, but it's really not. Like XDP is really designed to work together with the kernel. You can think of it like a preprocessor, and even like from BPF inside the XDP layer, you can access functionality such as accessing the kernel's routing table and use that information in the XDP. So that's really like working together. It also has like the same security model as the rest of the kernel. So you basically don't have raw access to the hardware. So it's still like protected in that sense. I think it's easy to deploy because XDP is basically shipped everywhere with distributions. It's enabled everywhere by default. And if you have the driver support, which by now, like the majority of drivers for 10, 40 gigabit and also 100 more, they support it. And so you can just get started without having to install anything else. And the other thing that is interesting also, it's really great because you don't have to cross the kernel user boundary, because you are in the kernel, you process things into the kernel, and that's like perfect when given you have containers, pods, and like the whole Kubernetes landscape, things like that. The kernel is basically the common denominator, and everything goes through sockets as a common communication bus, if you will. So that's really like a perfect match in that sense. And the other thing is, compared to kernel modules, where you would maybe have like a custom built IPv6 extension that you have in-house, maybe for load balancing or so, you don't need any of that, because like BPF programs, they basically have a stable API. So whenever you upgrade the kernel, things typically don't break. If they do, it would be a regression that would get fixed. So you can run your XDP load balancing program from a kernel, let's say 4.19 up to the latest 5.x, and they all keep working the same way. So that's really decoupled, which is nice when you develop this in particular. And also like whenever people are, like trying to extend functionality in terms of helper calls where you consult the kernel from the BPF program. So everything is really designed explicitly. It was like a explicit design decision that everything is built into the kernel and not extensible through modules, which also helps the kernel community overall to grow, because there's no special magic in BPF helper calls, and that way people are, if they want to extend it, forced to not keep their code out of tree, but like extend and help the community to grow overall, which is nice. And then again, like those programs compared to writing applications in C, maybe in user space, they are safety verified, and because of the eBPF verifier, so it's like more robust in that sense to write applications at that layer. I think we covered like the atomic swap case. Actually, there was even an interesting case that we experienced from the Cilium side. We had a large scale production user. They were actually by accident killing the Cilium pod. And they only noticed this like 30 minutes later that the Cilium pod is gone, but everything still kept working in the data path. And only later on, they did the restart of the pod, and everything, like was back to normal. But that's like really nice that you can decouple this, that you can atomically swap this at runtime.
Right, because the user space application loads that BPF program, and then that's there.
That's in the kernel, and that's like independent of what the user space is doing. Right. And that's also needed for upgrades or downgrades for applications, right? So, and then you can also basically, you don't need like an external TCP stack, like a third-party TCP stack. You can just rely on what is maintained for years inside the kernel that is maintained by and run in production and battle tested by Google and others in their fleet. So yeah, and the nice thing, or like, if you use, for example, AF-XDP inside DPDK, I mean, that really helps, I would say, like also growing and improving and optimizing the kernel drivers and the ecosystem there. And it removes duplication, right? So you can reuse all the tooling. That really helps both sides. And I think it's maybe now like more like a political thing inside companies, whether they should have like 2 driver teams, one for upstream, like for user space, and one for upstream kernel. But in general, it will, I think that's the way to go, like to reuse it through AF-XDP. And yeah, so did I cover everything? I think so, yeah. And basically in the case where we had like the Spectrum meltdown, this was also quite useful because like inside the kernel, you don't have this context switch where it really gotten even more expensive.
I think actually that's worth just drilling down a little bit more on like how the Spectre meltdown mitigations, what has that got to do with XDP?
Yeah, I mean, basically, so there are mitigations inside the verifier in BPF, and most of them are like for unprivileged, like for completely unprivileged user space, if people have that enabled. For example, there's a switch where you can turn it off entirely, which we also do in Cilium. But if you would not have that, and you would, for example, use inside your application a socket filter with eBPF, then the verifier basically mitigates and rewrites some of the memory access to avoid out of bounds speculation, for example. And for the privileged programs that are loaded through root, which applies to XDP, tracing, etc., because you can read the kernel memory, for example, from the tracing side anyway, like the really hard mitigations are not needed. And we do have some, for example, in the just-in-time compiler when we have indirect calls, but in general, XDP is basically being optimized, or like in general, like the eBPF in the kernel, to help whenever possible to transfer or like to avoid the overhead, for example, that you have through red booleans that are needed for indirect calls. So for example, like the verifier, it will go and track when you have like a tail call map, and your index, for example, where you then jump to the next program is always constant. It will basically, inside the BPF program, rewrite that to a direct jump offset rather than an indirect call, because then you don't need the mitigation because it's always a direct absolute jump. So yeah. And also like in the XDP layer itself, even there are optimizations, for example, calling into the BPF program, it will also avoid things like red boolean. They are typically, at least on when you have like high packet per second load, then they get more visible. But they are like mitigated as much as possible on XDP and the eBPF side.
Maybe you could actually explain what repoline is.
Oh, sorry. Yeah. So basically, that's a mechanism to catch like the CPU speculation. So for that target address, like if it's an indirect jump, you could potentially, it could guess if it's where like the next address is, if it's not available yet, and then it would go and execute those instructions. And later on, if it would notice that it's actually somewhere else, it would have to unwind all this information without any, let's say, user visible effects. But there are still like some effects in on the microarchitecture, because you have to pull in things from the cache, for example. So there are some artifacts that are still there that can then be extracted through a side channel, right? And with the repoline, you basically catch this in a sort of a loop that you avoid, like that the CPU goes to like an arbitrary address and tries to execute instructions from there, but rather it's like caught in a loop and, you know, like protects it in that sense. And we do have that in the just-in-time compiler as well for BPF for x86.
Okay.
Oh.
All right. So
I think we still
sorry, yeah.
wanted to cover some maybe more Cilium related things, maybe.
Yeah. Yeah, maybe we can talk a little bit more about the load balancer side of things. Yeah. So I think in this diagram, just to sort of clarify a few boxes. So service orchestrator in the top left, could that be Kubernetes?
Yeah, or like an external application. So for example, if you have like a, let's say, dedicated north-south load balancing box, and you push your service whips with backends, you manage those yourself, independent of Kubernetes, because maybe those are a different set of services, maybe connecting to legacy applications and so on, then this could also be like an own self-written orchestrator for those whips. But yeah, those are basically programming a Cilium API, which is then programming the load balancing table.
Right. So this is really saying my service, I have a service, and here are the backends that are associated with that service. That's what
exactly
the orchestrator is doing.
And then internally, the Cilium Layer 4 load balancer, you can configure this with Maglev. That's like earlier I mentioned like random selection, so that is problematic. We added Maglev basically in the Cilium 1.9, but if you have like a random selection, for example, and one of those nodes go down, then like the load balancing in front, which can be ECMP based, would suddenly select like a different middle node, like a different load balancer node that has zero context of that previous connection that just broke. And it will just select a new backend. And that is problematic because it's not robust. It will like kill the existing connections because TCP has no context whatsoever. And with Maglev, it's basically, it's a so-called consistent hashing mechanism, which means that overall, like the goal is here, like if that node goes down, the other node will still select the same backend and the traffic keeps flowing without interruptions.
I love these diagrams, that really.
And in order to do that, they all need to have the same sort of state for the load balancing. So there's like an algorithm which is calculating a Maglev lookup table where all the backends are basically in the same order for a given service. And when the packet comes in from the load balancer mechanism that is in front of it, it will calculate the hash of that packet, typically maybe like a 4 or 5 tuple, and it will then select for that given service a backend out of that Maglev lookup table, and then it will redirect it to the backend. And then the good thing is here, you don't need any state synchronization because like all the nodes that are even just spawned up, they will all select the very same backend here. So yeah, and that is basically used in the Cilium layer 4 load balancer as well. So whenever you program your services and backends, it will go to the Maglev service table. And that service table is basically, in the end, it boils down to a BPF map that is in the data path. And when a client does a request, it comes in through the NIC where XDP is running. It will select one of those backends through the Maglev algorithm and then push it to the other side, to the backend. And in our layer 4 load balancer, we basically have an encapsulation. So basically XDP, the XDP program there is also adding another IP header in there. And basically like that IP header's destination address is then the backend destination IP. The inner one is like the original client with service. And yeah, so that the reason for that is basically then the backend can process the packet and can then do the direct server return, which means it will directly push the packet back to the client without going to the Cilium layer 4 load balancer node again.
Right, and it's using that client source IP that's in the yellow box to
exactly
to do
for the reply. Yeah,
that's very cool.
So that's basically here shown in this picture. So basically it goes to the first, like typically there's an ECMP load balancing in front, and then it will go through a backend and then directly to the client with the response.
What does ECMP stand for?
Equal cost multipath.
Okay.
So it will basically select based on, for example, a hash, one of those nodes in the load balancing pool. And given you, and the nice thing is given you use XDP and I mean, I don't think typically that all the typical users are like Facebook, Google, or other companies like that at this scale where you really have to process millions of packets per second. The nice thing here is if you use XDP here, you can redirect those freed up CPU resources for other things. For example, you can co-locate other applications like your typical Kubernetes workloads on that load balancer nodes as well. So it's you are freeing up cycles for actual useful user stuff, right? That's what we want. Yeah, and what else? Like in the what we implemented as well, like for the load balancing, is a mechanism where you can also scale the packet that is then sent to the backends through RSS. RSS is called receive side scaling. So basically that means on a backend, when the packet arrives, it will typically on the network card side or like firmware of the network card, it will parse, for example, like up to the layer 4 of the packet, and then creates a hash and then distributes that through one of the receive queues of that NIC. And then like the CPU that is pinned to pick up traffic from that receive queue, it will then basically, like pick up that packet and process it on its own or dedicated CPU. If you don't have such thing, for example, in case of some encapsulation protocols that are maybe not supported by a given NIC, by mostly maybe older models, then it could happen if you have such encapsulation like the IP layer, that it would only parse like the first layer here, like it would only create an L3 hash, and then it will, like in the really worst case, everything end up on a single receive queue on that NIC, and then you couldn't spread the load. And so like the Cilium layer 4 load balancer, we basically have a mechanism where you can customize what is like a fake IP address in that sense, so that you can spread the load on the backend side as well.
Okay, right. So a couple of comments coming in. I think Yaron saying both session stickiness and backend service tagging, excellent. Grant, hi Grant, saying this is also cool. And Marius asking, is there some integration with the service discovery to route it? I'll start that question again. Is there some integration with the service discovery to route it within the Kubernetes node to the local service?
To a local service, yeah. I mean, that can also work together with the regular Kubernetes services, so that's definitely possible. It probably makes more sense in that case to use the XDP kube-proxy replacement, or like in general, like the kube-proxy eBPF replacement, because if you end up on the local node, it will work there as well. So it will detect that case and push the packet up to the stack so that it ends up in the right backend pod.
Right. Maybe talk a little bit about, we have these two sets of BPF at the socket layer and BPF at the XDP layer. So the XDP layer is, here's a packet came in from a network interface.
Exactly.
We're trying to deal with that really quickly. Talk a little bit about what's happening at the socket layer.
Yeah. I think it probably makes sense to get some context on the kube-proxy replacement first in terms of what we do there, because that may be like more straightforward to explain. And then we can go to the layer 4 load balancer. Like, for example, in the case of the kube-proxy BPF replacement that Cilium has, all the east-west load balancing traffic that goes from a Kubernetes pod to a different Kubernetes pod, if it tries to talk to a service, that's done on the socket layer. So we don't do any translation there in terms of per packet translation, like on the physical NIC, like with XDP, but everything on the socket. For example, an application having a socket open and it tries to connect to a service VIP, it typically calls like the connect system call. And then the kernel does all the rest, like TCP handshake, establishing the session and so on. And when that connect system call is taking place, there's basically a BPF program that is looking at the IP address and the port where the application is trying to connect to. And if it's one of the service VIPs that are in the like load balancing table that we have, then it's rewriting that connect call inside the kernel in BPF already to a backend. The advantage of that is basically that you don't need to do any per packet translation. Like the application itself, it thinks it's trying to talk to the service VIP, and the kernel itself, it's quite funny, it thinks it's trying to talk directly to the backend, only that the BPF program knows both contexts, and it does like that translation once at connect time.
Right.
Of course, for UDP, it's like on a per send message call, but basically like the BPF at the socket layer is like trying to manage those things.
Right, yeah. So I guess you could think of it as the socket layer being kind of closest to the application. You know, the application is making calls to the socket and we're trying to intercept those as quickly as possible and like redirect that connection to the right place. Yeah. Cool.
And for example, if you look at the kube-proxy case, if like the netfilter kube-proxy case, like worst case, for example, is an application is trying to talk to a node port service. So it's like sending it to a different node. Maybe even the backend is again on a different node. So it's doing like another hop until it reaches the backend. With that socket load balancing, like Cilium, the orchestration layer in Cilium that is talking to the Kube API server has all the context for that. So it can directly connect things and hook it up to the backend IP that is handling this. So it's like improvement in terms of latency as well.
Amazing. So just as we're getting to the top of the hour, we've got a comment from Yarin with like a explosion emoji. Amazing. My mind is blown. So I feel like that's a really good point at which we should probably try and wrap this up for now, unless there's any last points you want to tell us about for now.
Any last point? I think like one last interesting aspect for the layer load balancer that is maybe still worth to cover is that it also has like a PCAP recorder at the XDP layer. So often when you want to debug traffic and filter certain addresses or even CIDRs, normally you would maybe do that with TCP dump. But what we've built in here, like for the L4LB, is like a wild-carded match, where then the traffic is pushed into a memory mapped per CPU ring buffer, and then like user-based application. In our case, is actually Hubble. It's detailed in here. You can it will then pick it up and create a PCAP out of it. And if you do that on all the load balancing nodes that you have, you can basically get visibility into like where a certain connection is ending up on which load balancer, and like to what other next hop this is being pushed to. And yeah, so what you can see basically here is that we have inside BPF, on the BPF layer, a wildcard match in that sense. And you can use a Hubble record command that was added, but it's also possible to program this through an API itself, which is more flexibility here.
So Yaron just asked, are there any plans to incorporate those abilities in Hubble? I think that is a Hubble
That is Hubble,
command.
yeah, exactly.
Yeah, so I get maybe in the Hubble UI would be another possibility. Yeah. Yeah. I think that's super interesting. We got another cool emoji from Yaron. There's some great emoji game going on there. Brilliant. All right, so with that, I'm just going to say thank you so much, Daniel, for spending time and sharing a whole load of knowledge with us. I know there is more that we didn't get to, but that was super useful, really interesting, and we'll basically just have to have you on again. I think that's
yeah, it sounds good.
It's got to be the way. So with that, thank you, Daniel. Thank you to everyone who's joined us out there in the world from all around the world. Thank you for being with us. I'm just going to mention next week's episode again, because it's going to be about the eBPF for Windows implementation. So that should be like completely different and really interesting. Oh, quick comment has just come in. Suresh is suggesting that you should write a book about this stuff. So with all your copious spare time, right?
Yeah, it's like a trade-off, writing a book and coding, and like not enough time.
For sure, for sure. Right, so I think that takes us to the end of today's episode. Thanks again. Thanks, everyone. Take care, and we will see you next week. Bye.
Awesome. Thanks. Bye-bye.